Okay, in this video, I'm going to go over the first 10 problems in the review guide for Chapter 3. So looking at the first problem, it says use synthetic division. Okay, so we're going to use synthetic division, find the quotient, and if necessary, the remainder. Okay, so let's set this up. So a couple of things you want to be aware of. You're dividing by this factor, so that means that we're going to use the root, which is x equals 5. Okay, so that's number one thing. Always use your root. Here comes the root, and now I'm going to set up my division. Okay, so let's look at what I have. I have 3, 2, 1 is missing. So I know I have to put a 0 in there, and then I have my constant. So let's set that up. 1, -3, 0, and then -37. Now remember to bring this 1 all the way down. So the 1's coming here. 5 times 1 is 5. Add these guys together, and you get a 2. 5 times 2 is 10. That's a 10. 5 times 10 is 50. And you're going to get a remainder, and your remainder is going to be what? Looks like 13. Yes. So it's 13. So is 5 a root of the dividend? If it was a root, you would have had a remainder of 0. So you're going to say no, it's not. And why or why not? And the answer is the remainder is not 0. Okay, so you want to understand that piece of it. Okay, so now you're going to go through the next one. And it says, is x minus 2 a factor of this polynomial? Okay, so first thing, they have not said to you, use synthetic division. If you see the problem written this way, the tip-off is they're telling you you have this factor. You cannot easily factor that polynomial. So you're going to use that factor. So I want to get my root. So, excuse me. So let me get my root. I'm going to change colors. And I'm going to say, okay, the root is going to be 2. Okay, so just be aware of how I got that root. This is your factor. Set your factor to 0 to get your root. Okay, so let's set this up. I have a 2 here. Then I'm going to pull off the numbers. And I'm going to say 4, 3, 2, 1, blast off. I've got everything I need. So pull off all the coefficients. 2, 5, -8, -17, -6. Since all your work depends upon doing that correctly, it's never a bad idea to go and make sure that you have all the correct numbers and the correct signs. Okay, so we're going to bring down that 2 all the way. 2 times 2 is 4. 5 and 4 are 9. 2 times 9 is 18. That gives me a 10 down here. 2 times 10 is 20, and that's going to give me a 3. And 2 times 3 is +6, which results in a remainder of 0. So is this a factor? And you can say yes. And why or why not is that the remainder is equal to 0. All right? So 2 important problems right there. Okay, write an equation for the function graphed below. What is the minimum possible degree for this function? Besides the minimum degree, provide another degree that could be possible for this function. So you have 3 questions here, so make sure you answer all 3. So looking at this, when they say write an equation, what they're saying is you can write it in factored form. So a possible equation would be y equals, look at your first root. That first root is a -1. So therefore my factor is a -1, which is a +1, and because it's a double root, it's squared. Then multiply that times your next root. Your next root is 1, so it's going to be x minus 1. And then your next root is 2, and notice these are both single roots. It passes right through the x-axis. Then you get down to 3, and that is going to be a double root. So x minus 3 squared. So that's a possible equation, a possible function for the graph that is provided here. So what's the minimum possible degree? So what I have done when I analyzed my double roots was assuming that it was a double root and not anything higher. They could have been to the 4th power, to the 6th power, to the 8th power, etc. So when you assign a double root here and here, that's going to be the minimum. So then you have that double root, you have 1, you have 1. So we have 2, 3, 4, 5, 6. So the minimum degree equals 6. I could have also added 2, 1, 1, and 2. 2, 3, 4, 5, 6, gotten 6 that way. Either way, you'll get 6 as your minimum degree. Okay, next thing. What are possible other degrees? Whoops. So what you could have done, you could have said, oh, this double root over here, maybe that was another even root to the power of 4. So if that's a 4, so then I would add 4, 5, 6, 7, 8. So 8's another possible. I could have also made this a 4. If I did that, then I could have had a power of 10. You can't change the single roots, but you can, but your double roots can represent roots of other even powers. Okay, so that's the key thing there. So here are the 3 questions. Now, another thing you want to consider is this. Did I count my roots correctly? Well, look at your end behavior. This is up, up. If it's up, up, it has to be an even power. So therefore, that gives you more support that you did indeed count it correctly. Okay? All right, let's go to the next one. It says, let me just change my color. Write a polynomial of degree 3. Okay, so that's something I'm going to key in on. Having the zeros of 2 and negative 6i. Those are only 2 roots. What's your other root? You should be saying positive 6i. Present your answer first in linear factored form. Okay, so linear factored form is going to come first. So let me just get a highlighter here. So, because you need to know this terminology. Linear factored form. Okay, let's do that first. So if I'm going to do it in linear factored form, I'm going to say all my powers have to be to the power of 1. So this is x. Remember, you subtract your roots. And this is going to be x minus a minus 6i, so that's plus 6i. And then x minus 6i. All right, those are your linear form. So let me highlight that. This is a linear form. Okay, next thing. Take that linear form and put it in standard form. All right, so one thing I want you to always note is that this is a plus b and this is a minus b. So if I if I FOIL a plus b and a minus b, you will get, if you do it all out, you're going to get this. Okay, these will always cancel, so therefore I get this for a final answer. Now, we're not going to do this piece of it, because once we recognize that we have factors that will give us the difference of perfect squares, we're not going to multiply the middle terms, because on some of your problems, that's going to get so big that it's going to be a problem. And then you're going to get lost in the woods of trying to figure out how to get my numbers to go back into a standard form of some kind. So we're going to do this in a smart way. When I see that I have a difference of perfect squares, I usually handle those first. So I'm going to put it in a little box, and if my A, so let's do this. I'm going to say this is my A piece. So my A piece is going to get me x squared. Then I say minus, because I have a positive times a negative. And then if this is my B piece right here, it's going to be minus 6 times 6 is 36i squared. Don't forget to square your number. And then all of that is still multiplied by x minus 2, so don't lose that. Okay, so I've got those guys going. Okay, we're going to clean up the expression in the bracket. So I'm going to make some notes over here. I equals the square root of negative 1. Therefore, I squared equals negative 1. Okay, so with that in mind, my bracket becomes x squared minus, if this guy is a minus 1, it's going to flip that sign. And then I have x minus 2 here. Okay, so now you're going to have to distribute the x minus 2 to each of the terms inside. So this is basically a FOIL because it is a binomial times a binomial. So do your first terms and you get x cubed. Your outer terms give you positive 36x. Your inner, negative 2x squared. And your last is going to give you negative 72. Okay, so you should write this in standard form, which means do it in order from high to low of your exponents. Okay, so this, grab a little color here. So when they say write it in standard form, this is standard form. Okay, so that's the first 4. So let's keep going. Okay, this says use correct mathematical notation, state the end behavior of the function. Okay, so I look at this function, I see the highest power is 5. Remember, this is in standard form, so the degree of the function is just the power, the highest power. Okay, don't add those powers up because you're not in factored form. You're in standard form. This is the number you need. Okay, the other thing you need to see is what's the coefficient here. That's positive. So if it's positive and it's a power of 5, I know it's an odd function. So my odd function, how is that going to go? It's going to go in a down-up procedure. Okay, if it's down-up, that is going to give me a hint of what the end behavior is going to look like. So look at this end behavior. So say your function could look like this, okay? So for this end behavior, I have to write as x approaches, where is x going? X is going more and more negative in that regard. So negative infinity, what's happening to y? Y approaches also negative infinity. The next one, look at this piece now. X is going further and further to the right, and therefore it's going to infinity. What's happening to y? Y is climbing higher and higher, and therefore it's going to positive infinity. Okay, so memorizing these little symbols, these little shapes, helps me picture what my function looks like. Giving an answer that consists only of this will get you 0 credit. Okay, that's a way for you to think of the answer. It is not an answer. Okay, write in standard form. Okay, so I have factored. It's nicely factored for me right there. I see I have some complex roots. So what I'm going to do right away is spot the difference of perfect squares. If this is my A, and this is my B, then I see I have A minus B times A plus B. So I know the result is going to be x squared minus b squared. Okay, so let's do that. So my function's going to equal x squared is just the x times the, oh, excuse me. Let me go back and think of that again. Okay, I want x minus 2 because that's my a squared, and then a minus times a plus gives me a negative, and I times I is I squared. Okay, don't mess up foiling x minus 2. If you need to do this and foil it out, go for it. Okay, just don't think you can just distribute the squared to both terms. That's a mistake. So now what I'm going to do is I'm going to foil that out. This is x squared minus 4x, and then plus 4, and then minus, well, what's I squared? I squared is -1. So I'm going to do it like that just so I have my pattern established and that you're seeing where my numbers are coming from. A minus minus 1 is a plus 1. So my final answer is going to be x squared minus 4x plus 5. Okay, that is standard form. Notice how my x's go downhill from squared to linear to constant. Okay, that brings us to 7. Find the exact value of the zeros of h using any method. Okay, so you can just factor, but you want to key into the fact that this, my dears, is the famous 4-2. So therefore, you have a way to do this. So in class, what I had said that if I think about all these x squares as equaling z, I'm then able to rewrite this problem. So now I have z squared minus 2z minus 8. That's a regular factoring problem that I can now handle. So I say to myself, what multiplies to -8 and adds to a -2? Okay, so what's going to do that? So the multiples of 8 are 8 and 1 and 4 and 2. Okay, so I have to add to a -2. That means the difference between these are going to be 2. So that's my bingo. So those are the numbers I'm going to use. How am I going to use them? Well, I'm going to make them my factors, and in order to get a -8, I have to have one negative and one positive. In order to get a -2, when I add them together, that means that the 4 had to be negative and the 2 had to be positive. So this is not decomposition. These are the numbers you put in here. Okay, so you go right to your factors. And why do we do that? We do that because the leading coefficient here is a 1. So I didn't need to decompose the linear term. I can just go right to my factors. And now let's check my work. Okay, -4 times a +2 does indeed get me a -8, so that's good. A -4z and a +2z gets me a -2z, so I'm good. Okay, so you need to, it says, find the exact value of the zeros. So I'm not done yet because, first off, I just have factors. Secondly, I now am going to do my switch. Wherever I had a z, I'm going to replace it with an x squared. So that's 2 replacements right there. Then what I'm going to do is I'm going to set these two factors equal to 0. Now you could have factored x squared minus 4 into the difference of perfect squares. Or you can do this. In any event, you're going to get the exact same answer. Notice that the second factor is going to get me an x squared equals -2. That's something worth remarking about. Okay, I need to have 4 roots. When I take the square root of x squared, okay, take the square root of both sides, I get plus and minus radical 4. Don't leave it like that. It's a perfect square. But don't forget you're getting 2 roots. You need 2 from each of these factors. Okay, let's do the other side. Okay, so x is going to equal plus and minus. The plus and minus is key. The square root of -2. Okay, so let's do some work with this. This is -1 times the square root of 2. You can never, ever, ever leave this negative next to the 2 when you're working with this. Once you see you have a negative, you've got to bring it out. Okay, so what did I just bring out? That was an I. Radical 2 stays the same. So my end result is that x equals plus and minus. I usually is written first, and then radical 2. 2 roots there, 2 roots there, 4 roots, done. Okay, so be careful with this, be comfortable dealing with i's, recognize them, and work with them. Okay, number 8. Number 8 says to find the zeros of m by factoring. Okay, so they told me how I'm supposed to do it, so let's get rolling on it. Okay, the first thing I'm noticing is that I'm going to do greatest common factoring because I see that each of the terms has an x squared in common. So I'm going to take my function and factor out an x squared. That's going to give me back 2x squared, because if I multiply x squared times 2x squared, I get 2x to the fourth, minus 5x, because if I multiply x squared times minus 5x, I get negative 5x cubed, and then minus 3. Okay, so there I go. Now, remember I have to do this by factoring. This is a quadratic, so I'm going to have to do, that was my first step. My second step is going to be hard factoring. And I call it hard factoring because the leading coefficient right here is not 1. So what I'm going to say to myself is what multiplies to a negative 6. Okay, so what did I do? I multiplied this times that. That's how I got the negative 6. And adds to a negative 5. So where did that come from? Let me get another color. Okay, that came from here. Notice I'm taking the signs with them. Okay, so to multiply to a 6, the only way I'm going to do that is I'm going to say 6 and 1 or 3 and 2. So it has to multiply to a negative 6. That means in order to get a negative, one's going to be negative, one's going to be positive. So if I make, it looks like the bigger numbers have to be negative. So the one that's going to work is this guy, because negative 6 times 1 does multiply to a negative 6. And negative 6x plus 1x does add to a negative 5x. So I'm going to decompose this middle term, okay, and don't lose sight of your x squared. That's going to come along for the ride. This stays the same. My middle term now becomes negative 6x plus 1x minus 3. Okay, so now I'm going to factor. X squared is still coming along for the ride. Look at your first pair. My first pair has a 2x in common. I'm going to get x minus 3 back. Bring down that operation. I tend to just make these match because it's supposed to match if I'm doing it correctly. What number goes here to give me this back? And you should be saying a 1. Okay, what are my factors? X squared. Pull out the ones that look like factors, write them once. And then whatever you have not yet touched, 2x plus 1 is your other factor. Now, these are my factors right here. They don't want factors, they want zeros. Zeros are also called roots. They're called x-intercepts. Recognize every name. Okay, this guy gives me, set your factors equal to 0. This is a factor. This is 0, and it has a multiplicity of 2. Okay, so that means you can write it like that, or you can write it as 0, 0. This factor gets me a 3, and this factor gets me a negative 1/2. I need 4 factors. I have 0 twice. I have a 3. I have a negative 1/2. Done. Those are my zeros. Okay, 2 more problems in this video. Okay, the maximum number of turning points for a 7th degree polynomial is always 1 less than the degree. Okay, don't get that wrong, because a lot of people got that wrong on the quiz. So it's going to be 6. So it's always 1 less than the degree. Now, if you plotted a 7th degree polynomial and you didn't see 6 turning points, that's okay, because 6 is the maximum number of turning points. It could have fewer, but the max is going to be 6. Okay, so let's look at 10. Sketch the graph of a degree 2 polynomial with 1 0 of multiplicity 2, 1 0 with multiplicity 3, so that's an end behavior. Okay, so you have to have end behavior as follows. So it's going to be degree 6, so therefore it's going to either be up, up, or down, down. So it looks like, because these guys are both going negative, my function has to be down, down. Okay, it's even, it has to be down, down. So here's 1 0 of multiplicity 2, so that's 2 roots, 3 roots. I need one more root. So you're going to have to just find another root, and you can just add one, because the only thing they require of you is this and this. So that means that you must have, if this gives you 5, I have to have another single root. Okay, so if I know it has to go down, down, let's figure this out. Okay, so that means I'm going to start from down. So why don't I do, so I'm going to do a root right here at -3, and I'm going to make that have a multiplicity of 2. So I come up and down. Now I'm going to come up, right? That's my single root. I'm going to come here, and this is going to be my multiplicity of 3. So I'm going to put this at, say, 2. Let's put this at -1. And do I have what I need? It's down, down, so that's good. I have the end behavior taken care of. This has a multiplicity of 2. This is a single. And this has a multiplicity of 3. Okay, so that satisfies it. There are other shapes that satisfy it, but this one certainly does. So I hope you found this helpful.